And welcome. We are back for another virtual IoT meetup. Very happy to be here today with Alois from the Eclipse 4diac project. As you will see in today's presentation, there's a lot happening these days around industrial IoT and people trying to figure out how to essentially, in a nutshell, connect their PLCs and all their industrial equipment to the IoT. And it turns out that the Eclipse 4diac project allows to do just that. And there's lots of developments going on these days to make it possible to connect PLCs to the IoT. So before introducing and leaving the floor to our speaker today, I'd like to remind you that it's always better if you have questions to ask them as soon as you think about them. So please use the comments on YouTube, or you can also tweet them using the virtual IoT hashtag. This way, we'll make sure to get those answered. If you wait till the end, chances are we'll run out of time and we'll have to answer the questions offline. So yeah, feel free to also chat on the YouTube channel, right? You don't necessarily have to have questions. You can also talk with each other, right? So without further ado, Alois, welcome and thanks so much for taking the time for doing a presentation for us today. I think you also have a cool demo for us. So why don't you tell us all about Eclipse 4diac?
Hello, everybody. Hello, Benjamin. Thanks that I here today. Yeah, as Benjamin said, please ask me questions. I will try to answer them. And if we are not fitting all the time, we may then also put them in the forum and 4diac forum and discuss them further there. Yeah, not losing too much time, I will talk today about Eclipse 4diac and distributed real-time control. And as I'm very often asked, what is this distributed real-time control, what is all about, and what has it to do with IoT and Industry 4.0, I thought I'd start the talk today and giving a little bit of background about what is automation. And if you look in a classical textbook for automation, process automation, production automation, then you get something like that. So you get a picture where you see we have a technical process, and a technical process is something that takes an input like raw materials and energy and does something with this raw material and energy, and we want to have some desired product out of it. So if you think what could be a desired product, it could be the car you are driving. So I'm living not far away from a car production plant here in Munich. So this could be one of this technical process, but it can also be electrical power if you think of a power plant or a power grid or a warm house. And to make it a little bit more, so what we have here is we have building automation, talking about heating, energy, ventilation, cooling. We have machines that do things, that build things like mobile phones, cars, or full factories. Robotic applications and logistic applications like conveyor belts, like robots doing stuff in our plants. We have energy, what I already said. And the another big domain is chemical industry, like pharmaceuticals, like food and beverage. Brewing a beer is a very classical example where you have raw materials and energy and you get this desired product, your favorite beer. The only problem with technical processes is that the technical process doesn't do this by itself. So you need to have some control system which is using sensors to measure what is going on in this technical process and have actuators to influence what's going on. Actuators can be valves, can be motors, can be a heating element, can be a switch to turn things on and off. Sensors measure some physical property and translate it to something that the control system is understanding. And a control system nowadays is typically something digital, like a microcontroller or what in industrial automation is called PLC, which is a generic control device. And they come in lots of different flavors. I have here a schematic drawing of a few, and it can be like a an embedded board like the BeagleBone Black or an Raspberry Pi, which is also capable of doing some control, or it's very dedicated control device. So let's say a special Raspberry Pi developed for a chemical plant, or it can be special hardware like what you've seen here. And what's really coming more and more is that these systems are now networked together. So they have to interact because one of control device is not capable of doing all these things that it should do. And even further, and things that are coming along is, and Benjamin mentioned it, with Industry 4.0, with industrial IoT, we want to connect it with the cloud using IoT connectivity because we want to learn more about our control system. And not only about the control system, we learn a lot by that also on our technical processes. So how can we produce better cars? How can we use less energy for heating our buildings? These are things that we want to do, and this is why we need this IoT connectivity. So all the things you've seen here is not only because we can, and because it's cool, it's a lot of because we have some KPIs we want to improve. And a big pressure in industrial automation is that in the end, someone has to take his PC, his laptop, and connect the control devices and program them and configuring it. And and this is a very tedious job currently in industrial automation. You need lots of different tools, sometimes for each of the devices you're using, a different tool, different software, different knowledge, different programming methodologies. And especially this IoT connectivity is not well solved, not always well solved, better to formulate it. Also, even the connectivity between the devices is a hard task. And that's the reason we started some years ago Eclipse 4diac. Eclipse 4diac provides on one side an IDE. We will see today in the live demo, an IDE which allows you to develop distributed control applications, so where you really can handle many different devices using a modeling language called IEC 61499, which is not a good name, but it's an IEC standard, has been developed for more than 20 years, and allows us to do certain things that helps us to manage such automation systems. And the second main component of 4diac is the 4diac runtime environment, which we call Forte. And this runtime environment helps us to execute our models on all the different control devices. And we are currently already supporting quite a bunch of devices. You can see here, there are devices like Lego Mindstorms, Raspberry Pis, but also real PLCs like the PLCs you see here on the right side, like the PLC M1 from Bachmann Electronic, or this Avago PFC 200. And more up to come, so we are in our queue, we have quite a few. Some have already maybe seen that we are now supporting also Bosch PLCs. And yeah, if you think you have a device where 4diac should run on, I'm happy to hear about it, and we are very happy to support it. And one thing that we can support so many different devices is that we design Forte very modular with very strong platform encapsulation. We are supporting many different operating systems, as all of these devices you see here have really nearly different operating systems. Some are capable of real-time execution, some not. And we're also here working on new operating systems like FreeRTOS, which is used a lot in the smaller microcontrollers, VxWorks, which is very prominent, or RCX or Intime. And we were talking about communication, and communication is also a very important feature for 4diac. So we have already worked on many different communication protocols which are coming out of the box. This is classically TCP communication, Ethernet communication, but also things like MQTT to get this IoT connectivity, or what we already have a prototype is OPC UA, which is getting more and more popular for industrial automation. So before going to the live demo, I would give you a very quick introduction what this IEC 61499 is all about. I'm teaching now 4diac and 1499 for many, many years, and I learned having a rough idea helps you to better get an understanding how to work with 4diac. So in 4diac, it's a modeling language, IEC 61499, it's a graphical modeling language. And the main element, a component or a class, how you would call it in classical programming, is called in industrial automation function block. And the function block concept is not something new in industrial automation. We already have it in a previous standard called IEC 61131.3. And this has been extended to better support encapsulation and also to better support distribution. And it has been extended with an event interface you see on the top. So 1499 function blocks are passive. They are in your application and wait for events to do certain actions. And this is a very interesting concept, especially when it's coming to distributed and networked control devices, because now you can synchronize yourself to network messages, and you can, as application programmer, define in a graphical notation when to send messages on the network. I will briefly go through how function block execution is working. I already told it's passive, so we are waiting that an event is delivered to the function block. When an event is delivered, we're sampling the inputs. This is very important for having stable data for the encapsulated control functionality. So there is some functionality encapsulated based on events and internal states. This encapsulated functionality is invoked. And based on the result, one or more output event is produced. And this is the basic model how these function blocks work, and with that you can do a lot. So when you have now a library of function blocks, and this is what we're today looking at, so you can take these function blocks, wire them together with events and with data, and model with that the functionality. And an important property of the IEC 61499 application model is now that we are modeling applications independent of the hardware. This is something that is a new concept in industrial automation, because normally you're going to the device, program the device, and then program the next device and think about how they should communicate. When you have such distributed control applications, it's better to model them like this, because what you can do now is you can have the full functionality in mind. But this is important. We also need some hardware. So in 1499, we have then a system model where we have devices. In this case, an example with 5 devices. The devices are connected to the process, to the machine, and they are networked together. And this is a model which allows us to say what kind of devices we have, how they are communicating, and how they are connected to the process. In devices, we have so-called resources. Resources are a grouping. This is especially interesting when you are developing bigger applications, because resources are shielding their execution from itself. So if you look inside a resource, what you can see here is that the resources are finally the elements which will execute the function blocks. So the resources are in charge of delivering input events, transporting output data to the according inputs. And we have special function blocks which allow us to interact with then communication with the network interface or with the process interface. So function blocks like function block B or E would take the process interface to talk with sensors and actuators. This is a very important concept, and because everything is encapsulated and allows us to be, it's not implicitly, it's always explicitly specified, which is quite important when it comes to correctness of your applications. And what we then need to do is we need to bring together both models. So the first model is the application model what we had. We had a second model, the system model. And by mapping, this is the process of distributing your application to the devices, we can now assign where the function blocks of your application will reside during execution. And this is normally not done just for fun. Normally you have some rules where function blocks are located based on the available sensors and actuators, and or based on maybe network resources, network bandwidth, or the power of devices. What's also possible is that you have several applications in one device, because in a distributed system, it can be that different parts of the system are implemented by different people, and this is also accommodated in the model of 4099. When you look now at how I modeled in this example, the mapping, then you notice that function block 1 and function block 2 and also function block 5 are located all in different devices. And so the connections between them have to go over the network. And if you look after the mapping into our devices, into our resources, you will notice that both function blocks, in this case, as example, function block 2 and 1, just have these small parts where to inform you that there was a connection which is now interrupted. And on top, you still have your application model that is undisturbed, but in the devices, you have to do now something. And there are options that you then generate or model the communication, how the function block, the connections between the function blocks are then handled over the network. So in this case, we inserted publish and subscribe function blocks. So a subscriber takes messages from the network, hands it over to function block 1. So it delivers the data it gets from function block 1. And the outputs of the function block 1 are then put by the publisher on the network. And on the other side, we insert a subscriber to receive this output and hand it on to function block 2. The great advantage of this approach is that your application model, as I said, is not disturbed by that. So if, because of any reason, the device is removed, an additional device is added, you just change the mapping of your function blocks to the devices. And just remap and reconfigure the communication, which is much easier than if you're just programming devices and then a device is removed. This is one of the great powers of this device independent model in the application. Another important feature is if, for example, function block 1 is a function block interacting with the sensor or an actuator, then typically in industrial automation, it can be that it's very lately in the development process finally fixed at which address or at which input or output the sensor will be connected. And therefore, we just configure the device-specific parameters down here so that at the very late stage, or even when it's changing, we don't interfere with our application. And that's a very, very interesting thing. Again, helping you for late changes. So this was the very, very, very quick overview on 4099. There is a lot more about, especially how to program function blocks, how to do further higher level concepts. I'm happy to talk with you about these in a separate session. Before going into the live demo, I want to talk a little bit about how the 4diac toolchain all work together. So we have here a 4diac device, for example, maybe an PLC, or what we will use later, a BeagleBone Black. And in order to program this, we need our 4diac IDE, and currently we need the source files of our runtime environment Forte. And for the function blocks you develop, you need to generate C++ code, take the target compiler, compile it to a platform-specific version of Forte, and download it into your PLC. However, this platform-specific version of Forte does not have a specific control application inside. Instead, you can now model the control application as we have done it, or as we have shown it in this overview, and download it as configuration to your PLC, to your control device. And you can also change it. And this is very powerful because you can use this for rapid prototyping, for developing your application, change it, test it. And hopefully with the next major release of 4diac, you even don't need to do this nasty path on the right with the C++ code generation, but we are working on a way that you can do all the application and type download via the left path through the application download. Okay, the next step now would be that I start with a very simple example, which is a blinking light. And for that, I switch to a 4diac IDE. And in the 4diac IDE, I would like to, so this is how 4diac IDE looks like when you start it up the first time. It's the latest version, 1.8.4. And what we want to do is, and for that I have my webcam here, is I have this BeagleBone Black with a simulation of a traffic light. So we have here the red, orange, and green for the car light, and here the red and green and the push button for the pedestrian. And today, as we have a little bit limited time, we at least want to get the orange LED for the car light blinking. So for that, I start a new system. No, I don't start a new system because I cannot click anything. What's going on? Ah, no. New system. Okay. And it looks like that my PC is a little bit overwhelmed by all the stuff running here. Good, Blinky is here. And in Blinky, we want to have an application. As I told you just a few minutes ago, the first thing is to have an application where we start from. And on the right side, you get a set of function blocks, which we are already delivering with 4diac. So this is a set of function blocks like function blocks translated from the old standard. There you have lots of like timers, like edge detection, counters, things like very basic things which you need a lot. And another set of function blocks which I want to use today is the event function blocks. And the event function blocks are function blocks normally used to manage event flows through your application. But with them, you can also do quite cool things. So small control tasks can directly done with them. So for example, for our Blinky, we have here a function block called eCycle, which is delivering us here with a separate, with a given cycle time, let's say every second, an output event after it has been started once. So for holding the state of our LED, we take this flip-flop. It's a set reset flip-flop. When somebody sends a set event, it will set Q to true. And if we get a reset event, we will reset Q to false. And we need an eSwitch. The eSwitch is used for switching the event flow. So when an event is coming in, it looks at its input G and decide if G is true, it will forward the event on output 1. If it's false, it will forward the event on output 0. And in our case, we want to take the current state of the LED, and if the current state of the LED is true, we want to turn it off. And if it's false, we want to turn it on. So, okay. And we want to write this to an output. So we have here IO function blocks, and one function block which we want to use is QX. Q stands for output in industrial automation. and X is for Boolean values. So this function block will update our LED every time it receives a request event. So we have here an input that says if it should initialize or deinitialize. And we have a params, which is telling which output of our Raspberry Pi we should use. And to be honest, I have to cheat a little bit and look in my old standard application. The orange light has output 60. So we will write here and 60. Good. So this would be our application. If we would have now a simulation environment, we could directly test if this thing is working. But I want to show it for you on the real hardware. So I go here now into the system configuration, and I take a BeagleBone Black as hardware. And this BeagleBone Black comes with a parameter called manager ID. And this is somehow in this IEC standardization phase has been developed as way to specify how the engineering tool, 4diac IDE, can connect with the device. So, and our device, if it's working, should be located on this IP address. And per default, 4diac devices or 4099 devices are listening to port 61499. Okay, and you see we already have some resources here. Good. So the next step then is to assign the mapping process, the function blocks to the hardware. In this case, it's very simple because we only have one resource, so we can only assign it to this one resource. What you see here is that function blocks have now changed their color. So if you have a white function block, like this one, you know that either this is some placeholder or something where you still have to do something. And each device that we are adding to our system configuration gets a different color. So I can show you, for example, the system configuration for our traffic light. You see here 4 different devices, 4 different colors. This helps a lot when you look at bigger applications to see where, no, this is all on one. If you look at bigger applications, you can see here is something on a yellow device, in the middle is something on the blue, and this pinkish device are these 2 function blocks. So this helps you to keep track of what you're doing in your big application. Okay, so there is just one thing I want to clarify. And we have then several perspectives. So the perspective we have been working so far is the system development perspective. And the next perspective we're working on is the deployment perspective. And the deployment perspective has here some helper if you want to do local tests. We will see if we'll need this. And we can do remote tests, like we can select the devices we want to download. So in here you see all our systems. This is the Blinky I just did, and we can select that we want to deploy this device. And by pressing the download button, perfect, 4diac is sending a set of configuration commands down to the PLC device, or in our case, the BeagleBone Black. And this is devices like create me an instance of the eCycle, write the parameter 1 millisecond, create connections between them. And this is what I meant before when I said, okay, we can now change it. So you can send the next command like adding a new function block, removing a function block, changing a connection. And this is the great power of this modeling language and how we implement it in 4diac. So, as you can see so far here, the orange LED is still not blinking. So we may want to look into our device and see what's going on, why nothing is happening. And for that, we have a feature where we can go online with the system. So here in the debug menu, we have a monitor system, so we can go into the Blinky, and we can go now in our application and watch what's going on. And what we see here is that so far our QX function block has received 0 inputs. Events have always received false. So the first thing, I did it on purpose. So normally you would write via the init and the start of the eCycle to some startup logic. But I wanted to show you this feature. So this is the reason I did this. We can now select our event and want to trigger it. And what we see now is that we received an output event, we got as response, it is working. And so we can now see if the LED is blinking. And hooray, I hope the video quality is good enough. So I can also hold it a little bit up. So you see here now, my orange LED is blinking. So this is a very simple example, and I hope you forgive me that I did not something very big, but it's a very good one to test now things. So what we could do now is that we could add a functionality to count how often has this LED been turned on. Because turning a lamp on in, let's say, a street light, or if you have a big commercial building, it's very often important that you know how often has a lamp turned on, because maybe you have to change it so. So we can have here a function block called ECTU. And we want to have a function block ePermit. And this function block will forward events only if the value is true. So what we could do now is we could select this to the ECTU. I will just go offline. And I say I want to map these 2 function blocks also to our BeagleBone Black. And maybe this is now, I'm doing a small experiment with you. So you see here our LED is still blinking, so I haven't done anything to it. And what I want to do now is I want to add this functionality to my existing device without disturbing it. So normally when you're doing PLC or embedded programming, what you would do is you have to switch off your program, you turn it on, download your application and turn it on again. With 4diac, we have a feature which is a little bit experimental. So let's see if it's working. We can now online create these function blocks. We can start them. We can online create this connection. And we can also create this connection. And you see here, the LED is still blinking. So, my finger. And we can see now if it's working. So, and you see, I just added a new functionality, counting that while I was downloading it, it already had 11 turns on and offs. And the next step would be, which is not working with this board because it's just connected by a USB to my PC, but we could now say we want to publish this value via MQTT. And for that, we would insert here a publish function block, which would be this one. And as we want to have it as raw value, we would translate it to strings. So we would like to have, and what is this value? A new int to string. And we would like to have this value sent via MQTT over the network. And we could do this here by just specifying that we want to send this as raw string value over MQTT using it IoT or TCP /IoT.org. We want the client ID and we want to have a tag 4diac /LED on. It looks not perfectly nice, but we could just add this here, download it, and we would have would publish this value with MQTT. For this example, as my BeagleBone is not directly connected to the internet, it would not work. But I have something a little bit more elaborate. This is the second demo, which I've brought with me today. Where is it? It's this one here. Is there a question, Benjamin?
I was about to ask just that. If people have any questions, please make sure to ask them to Alois.
Yeah.
I don't think
so the second demo is a steam boiler where we have a SCADA system which provides us a set point for the level of the boiler and sets the steam demand somebody's taking, how much steam somebody needs out of this boiler. And so this is a little bit more sophisticated control algorithm. It's closed loop. So there you have a level controller measuring the level, taking the set point, have then a correction controller taking the current flow of the water and the current steam flow, calculating then a set point for a valve, which is letting water into this boiler. And as I don't have a real steam boiler with me, and steam boilers can be quite dangerous, especially if there is too much steam and too much pressure, I have a simple simulation of this boiler. And what this boiler is producing and is, I just go relieve my system a bit. So this is the boiler example. And what this boiler is doing, and you see I have been online with this boiler. I just go online with the boiler. So you see that I'm here also online. So this application is already a little bit bigger. I just make it so that you can see a little bit more. And here is a very classic control algorithm. It's a PID, which is getting the set point, which is currently 450 for our level of the tank, and the actual level is jumping around a bit. And the reason why it's jumping around is mainly because we have some noise in our measurements, and we have some pressure problems in this tank. So you see here it's jump, and this is the, let me see, this is the feed water flow. So you see here the feed water is flowing a lot, the tank level is jumping around a bit. And what do we have here? Here we have the steam flow, and we also have some pressure fluctuations also in the steam flow. And the simulation is handling this because it has showing some physical properties with that. And what you see here also is that we have here some publishers which are publishing the whole thing to MQTT. And if you want to go live on MQTT, on IoT-enabled.org, you can watch the tag 4diac boilers hash. And where is it? So they are currently, these are the values that are currently published. So we have here 5 values that are published. And you see jumping them around. But I'm very much like the figures, like which MQTT SPI is giving us. This is very convenient. First of all, it was very easy to set up. And the second thing is I can already see something. So I can see that the tank level is, it should be 525 or so, or 550. So there is definitely an issue with this tank because it's not, it should have reached by quite some time the tank level. So there needs to be some tuning of the parameters. So maybe there is a set point not correct, or a parameter of one of the values not correctly set. So what we could do here is we could go into our 4diac application and see where there are some values that look not good. And I'm not perfectly sure, but I think it should be, for example, this value should not be 0. And we can cautiously maybe tune it here. Let's see. And hopefully it will improve a little bit, at least, our control algorithm. So the lows should go away and we should gradually move a little bit up. Maybe it was not enough, so we can try it with one. Maybe not. So still there is some open values for tuning this algorithm. This is one thing. Another thing what we can see, and this is now interesting from a maintenance perspective, if you look at the feed water valve. So this is the movements of the valve, and 10 means fully open and 0 means fully closed. And what you see here, within a few seconds, it's going from fully open to half open to nearly closed. So this is a high friction on this valve. So when I see this, I know that we definitely need to improve here on some values, because either there is problems with the measurement or there is problems with something else which has to be compensated for. Not the tank level. Yeah. So, and this can now be analyzed, can be worked with, and this is just a very quick and short introduction to what capabilities 4diac helps you, gives you, what possibilities you have, and I hope it was interesting for you.
It certainly was for me, and we have lots of people watching and already sending questions, actually. And I have a few myself as well. One is from Eric, and so you mentioned a few use cases already with the pedestrian lights, the traffic light system, the boiler. Are you taking 4diac and this technology into building automation space? Is the question.
Currently, myself not. I know that people are investigating, so users of 4diac are applying 4diac and 4diac related technologies a lot in building automation. Especially because with the function block concept, you can model typical tasks in building automation and duplicate it very easily. And in building automation, you have often a lot of controllers. So there is a great interest. Personally, I'm currently not, but if there are projects, I would definitely go for that.
Which actually brings me to one question. I'm no building automation expert, but I'm pretty sure there's a bunch of communication protocols that are specific to building automation, just like there is other protocols specific to other domains. So can you maybe briefly elaborate on the protocols that are supported today in 4diac, as well as maybe other protocols that you aim at supporting in the future?
So from the building automation perspective, to be honest, we are currently from the protocol support rather low. I think the biggest is QNX and EIP, which I'm currently haven't had a look on it. I know that there are some open source libraries for that, so it could be an interesting look.
Look, the question is more like, what are the protocols supported today in 4diac? I believe you have things like Modbus, OPC UA. So maybe if you have...
Yeah, exactly. Look, what we have is, and I think I had it on one of my slides, but that was maybe too quick. So currently we have Eclipse NewsCADA. I should change this here. Eclipse NewsCADA SFP, which is a small protocol from the Eclipse NewsCADA project. We have classical Ethernet TCP UDP, where you just send UDP multicast messages between 4diac device, which is maybe less reliable, but very easy to set up, very fast, very low overhead, quite interesting. Ethernet PowerLink is an industrial Ethernet field bus where we are acting as master. So you can, when you're using the Open PowerLink library, you can connect your 4diac control device with sensor and so I/O modules supporting Ethernet PowerLink. We have quite some experience with Modbus TCP, currently only as client. I know people are always asking also about server, which would be the slave. If anybody on the line is interested in supporting us for that, please contact me. This would be very interesting. You've seen MQTT. OPC DA is also quite interesting. And also quite interesting, although it's really old, it's RS-232, so serial line. We are using this, for example, in Vienna, there's a laboratory course for students using 4diac, and they are connecting to a measurement device, reading out the values, and based on the values read from this measurement device, do then some control actions. And for us, very important, and this protocol is now coming to many, many different places. So it's not only industrial automation, it's building automation, it's chemical plant automation, it's energy automation, it's OPC UA. So this is very coming, and this is what we currently have.
Okay.
And if you go on our webpage, it's quite easy to add new protocols.
Yeah, actually, maybe that's a good point. I don't know if you have a slide with some links. Otherwise, we'll put that in the description of the YouTube video.
Oh yes, please. I completely
like some tutorials, some links for people to learn more and to download the code, etc.
One thing that just came to my mind. Yesterday, someone pushed 5 or 6 changes that 4diac will also support ROS. Which is the robot operating system, which is an open source middleware for robot applications.
Oh, nice.
Yeah, very nice. I was waiting for that quite some time, but it was not so easy to get a grasp on this topic.
Right. So another question from Emir, more on the tooling front. When there are lots of systems and lots of devices and the solution is made of many devices, are there any shortcuts in the tooling to help send similar codes to the devices and like simplify the communication when there's really lots of information that you need to? I guess the bottom line is how or does the tool help not having millions of wires on in the IDE going from one system to another?
Yes, it helps. There are a few things in the language. One thing is when you look, for those who downloaded 4diac IDE, we tried it in the traffic light example. There is green lines, which I haven't talked today about. Green lines are cables. So with the green line puts several event and data lines in both directions into this cable. And so you have an interaction between 2 function blocks. So here, for example, it's the real application of the crossing controller. So here you have the crossing controller managing the full crossing. And here you have a function block that is just managing the 3 lights of a car light. And via this line, they are going, I think, 3 events from the crossing controller to the car light. These are like go from red to green, go from green to red, and go into off mode, which means blink orange, at least in Germany. And and backwards are going, I think, 2 or 3 lines like I did this, I'm red, I'm green, and I'm offline or something. And you could add here more, you could add here status information. So this is the first thing which helps you to keep your application a little bit more tidy. The next thing which is still possible is that you can now group stuff here into sub-application, it's called. So you can just take a few and say this is a subsystem. Say like this is a subsystem. And it will be just hidden with, sorry. I'm not very good with this thing. So this is now grouping, and you can go inside and you see everything that's inside. This is in the current stable version, unfortunately, not very well supported. And this is where we are currently working a lot where we had just the first milestone release last week, because exactly this is a big issue to bring to help you in structuring your application, and with sub-applications this is working much better.
Okay, so there's a question from Rodrigo, which I hope I will reformulate properly, and I will probably actually ask a slightly different question. But so you demoed the integration with MQTT. I think some people might feel like more is needed in terms of modeling the data, making sure that on the other end, people consuming the data from the MQTT broker might have a hard time figuring out what kind of units the data are expressed in, that kind of stuff. So do you have any plans on integrating with, I don't know, technologies maybe like Eclipse 4diac for modeling the semantics of the data, and maybe have some kind of typing, so as from one end to the other of a system, people would be able to figure out what kind of data really is flowing in the system?
We are experimenting a little bit with that topic in OPC UA, because with OPC UA this is coming a little bit more natural. Where I'm missing this a little bit, where to store this or how to load this information in 4diac. What could be done is, this is a thing that drives me around a lot. I had a first discussion with Eclipse 4diac people at one of the last EclipseCon I have been. Unfortunately, my time was not enough that I spent on this. But yes, I think it's an extremely important thing. So as you have seen in my example, I was just sending raw strings. And for improving system integration and future IoT applications, we need something like that. And I'm happy for any suggestions how or what we should do here, especially with MQTT. OPC UA has here some better base from the object model, but anyhow, anything is more than welcome here.
Right, and actually Rodrigo provided a bit more details regarding the question, so I apologize for not getting it right the first time. The question was also around like the MQTT integration within 4diac. How does it relate to the standard, to IEC 61499? Is this additional function blocks? Is this 4diac specific stuff? Could you describe how the MQTT stuff and all the IoT stuff that's been added in your demo, how does it relate to what's in the standard?
The standard itself is completely agnostic about communication. Or no, sorry, that's wrong, about communication technologies. So the standard itself defines that we need communication. It also defines communication function blocks and defines them generically. So the standard itself defines that when we look at our Blinky application, that we have something like publish. The standard defines something like we have subscribe. And it says, okay, subscribe can be used. I'm just looking for the publish here. So I could add here a publish. No, sorry, I would like to have a subscribe. I could add here a subscribe that is giving me, every time I get a message on the network, I want to turn on my Blinky. And the standard does not define how the data is flowing on the network. It's just an interface to this communication. And what is 4diac specific is that we are wrapping different communication protocols behind these function blocks. Because the standard, if you think about that, 4099 has been started in 1993. The first version was publicly available 2000, and 2005 it was standardized. And in 2012, we made the second edition. So a standard like IEC 61499 needs to be separated from different communication protocols. Otherwise, it would be obsolete every 2 years. And this is another thing, what I like on IEC 61499 is that it helps me to abstract away the hardware. So I just stop here my MQTT spike because my PC is getting slow.
All right. So yeah, that makes perfect sense. And I hope this answers Rodrigo's question. I actually have one last question myself, and I think it will be time to wrap things up afterwards. Is there a better name or a human pronounceable name for IEC 61499, or do people always refer to this as IEC 61499, which is always difficult to pronounce?
You speak from my heart. Maybe I have to add here that since 2 years I'm the convener of the standardization group, and I spend a lot of time thinking about this. The standard itself has a name, and the name is called function blocks. However, this is very generic, and in industrial automation there are at least 3 or 4 standards on function blocks. And so far we did not have any other name, but I would be happy to have one. Unfortunately not.
Yeah.
We often say just 4099, which is a little bit easier to spell, and skip the 6.
Right. That makes sense. I'll keep that in mind. Well, thanks very much, Alois. If people watching the replay, watching the recording, have questions, please make sure to post them in the comments, and we'll send them to Alois and make sure they get answered. Also, we mentioned that there will be a few links also added to the description for you guys to get direct pointers to download 4diac and to learn how to create your own, implement your own protocols if that's what you're interested in. I think we'll be back on March 8th. The webinar will be about reactive blocks. Yet another tool, I guess, for visual programming with a slightly different approach. What else? Well, yeah, if you have any comments regarding the meetup, if you'd like to see other topics, if you have suggestions for talks, feel free to reach out. Send us an email, iot@eclipse.org. Feel free to review also, to give us your feedback directly on meetup.com. You can give us 1 star, 2 stars, 3 stars, 5 stars, and what's more, give us feedback. Tell us what you think, what you'd like to see. We're always looking for that. So thanks again, Alois, and we'll be back in a few weeks. Thanks, everyone.
Thank you.